Hello, and welcome to another session on data mining. Today, we are going to be building linear models from scratch. We have covered all the fundamentals, all the prerequisites for doing this. We have covered uh, gradients, we have covered gradient descent, and now we are in a position to go ahead and put all of those ideas together and build these linear models from scratch. Before moving on, let me just give you a brief recap of what we have done in this module so far. So we have talked about classification, which is we want to assign types or classes to a given object that is given to a machine learning model, which is called an example. So we extract features from each example, we show them on a feature plot or a scatter plot, and then we want to make a rule, which we call a classifier, in order to discriminate between different classes. Now we can have a single discriminant if there are two classes only, let's say the positive class and the negative class, then all we need is a single discriminant function. If that discriminant function is linear and it is able to generate 100% accuracy over the training dataset, then we call that particular classification problem or that dataset is linearly separable. Now we know that all datasets may not be linearly separable, and we saw some examples of those in our previous discussion. But linear models are a theoretically very sound way of understanding machine learning, and then they can be extended to cases in which the dataset is linearly not separable. So it provides a very good foundation for you to stand on in order to understand more complex models in machine learning. So any questions you have regarding these, why we are studying these, I hope those are answered by now. The primary goal is to give you a strong enough foundation that you'll be able to understand more complex models as we go towards them in the rest of this module. So right now, I'm going to start off with, on your screen is a single data set that we have already discussed. This is what I call the AND classification problem, in which we want to classify the examples with features 1, 1, which is over here. Oh, sorry, I seem to have lost my cursor. Uh, Over here, this one. So this is our example 1, 1. So for this particular example, we want to generate a prediction label of +1, +1. And for all these examples, we want to generate labels of -1. So this is a binary classification problem. What we are interested in is finding a function that can separate these two classes, the blue circles from the red one. So this is the AND classification problem. And we have covered this in our previous work. We were able to identify a line, and then we were able to identify the equation of that line using either mathematics or geometry, using either algebra or geometry to get there. Okay, so up till now in this particular problem, we have built a linear discriminant that allows us to separate these two classes. If this were a classification problem with more than two classes, let's say if we had three classes, then we would need more discriminants. And we would then combine those discriminants in order to generate a classifier. But for the very basic case that we are going to take for probably most of this module, is going to be binary classification, because if you understand this well, moving on to multi-class classification is no big deal. Okay. So in this particular case, what we did is we represented each example as a set of features. So the features for this one are 1, comma 1. The features for this example are 0, comma 0. This is 1, comma 0, and then this is 0, comma 1. So this is a very simple, very basic classification problem, and we can solve it, and we have actually solved it through either constraint satisfaction or through geometry. So we have, sorry for that line. Um, we have represented each example as a set of features, and for the discriminant, we have chosen a linear function because there are only two features. Therefore, d over here is equal to 2. So therefore, our discriminant function simply becomes w1x1 plus w2x2 plus b is equal to 0. Okay, and our objective, as we've discussed earlier, we want to reduce the misclassification error. So we want a line. If we take a line like this one, for example, let's call this line L1, then this is generating errors because some of the points that are above the line should be below the line, these points, these 2 points. And so there are two misclassifications that this line L1 generates. And we've discussed how we can change these parameter values, these W1, W2, and B, to get a line that gives us no classification error. So that would be a line something like this, and we have found equations of that line. So in terms of our REO or REO principle, we have representations. We have a representation for the examples, which is features. We have a representation of the machine learning model, which is essentially a line in this case, if because there are only two features. If there were more than two features, we would have a hyperplane if we were using a similar form like this one. In terms of evaluation, which is the second step, we are using misclassifications. And the third step is optimization. We are interested in finding a line that minimizes the number of misclassifications. So this line, let's call this line L2. L2 produces less misclassifications than L1. Therefore, this is a better classifier over this particular training data set in comparison to L1. And we did this optimization or finding these parameter values, W1, W2, and B, using visual reckoning or geometry or constraint satisfaction. So we have essentially covered all the basic requirements, R, E, and O, of building a machine learning model. And we've already discussed why we are interested in studying these linear models, because they give us a very rich theoretical understanding, a theoretical background that allows us to build more complex models in the future. However, what we probably cannot do is, once the problem becomes too complex, we will not be able to use this visual reckoning or this constraint satisfaction or trying to sort out the line by hand. If it's two features, the best method that you can have is, of course, identify the line visually, right? And that we have done already. But what if we have three features, or what if we have 1,000 features, or what if we have 1 million data points given to us? Then we will not be able to solve for these by hand. And as a consequence, we would need some computers to help us, unless you're really smart. Okay, I don't doubt that. But anyways, what we want to do here is to build a mathematical model that allows us to implement and solve for these classification problems on a computer. Okay. So as we've discussed, we'll be using these linear discriminants, and the general form of linear discriminant is given by this equation. This is a function of two variables. We have an input example, a feature representation of the input example, which has D features. Let's say if you want to classify a pizza of whether it's good or bad into these two classes, good or bad, then each of these features can be a feature extracted from the pizza itself. It can be what type of dough you use or what type of toppings you have, and each one of them can become a feature. So you can have, in general, a set of D features. Okay, and we have, as an input to this function, we also have a set of parameter values, which we call the weights and the biases. So this particular W vector is composed of these D different dimensions of each of weights, and each of the weights is multiplied with the corresponding feature. So W1 is multiplied with X1, W2 is multiplied with X2, and WD is multiplied with XD. And then we have got a bias parameter B. Now, I'm going to write this in a more compact form using what are called dot products. And I'm sure that you're familiar with dot products. You have studied them in high school or later. And the way these work is, if you are given two vectors, let's say if you got a vector W and if you got a vector X, then what you do is you multiply the corresponding elements of these, and then you sum them up. Now, throughout your machine learning experience in the future, if you see dot product, if you see sum of products, just like this one, you can express that as a dot product, which is W transpose of X. So you lay this down, this vector W1, and you multiply the corresponding elements and you sum them up. So that is what W transpose X means. So this representation, this long addition of these products, pairwise products, can be expressed as a simple dot product. And then you have got a B parameter, and you put this equal to 0, and that then becomes your linear discriminant. An even more compact representation of this whole thing can be in the following way. If you look closely, then you have these D features, which are each of which is multiplied by a corresponding weight value. So W1 gets multiplied with X1, W2 with X2, And then in the end, you're left with b, which is not multiplied with any feature. But if you replace that by a multiplication by a 1, then what you get is a dot product like this one. So you can have a dot product of a vector called w prime, in which each of the original weight components is there, w1 to wd, and then you have an additional weight component called the bias. And in the corresponding features, what we have done is we have added a 1. So if you multiply this with this, you get w1x1, you add it to w2x2, you add it to wdxd, and then you add b multiplied by 1, and then this becomes an even more compact representation. Some people may drop this plus b part, and they can just say that it's already included within this representation. So if you see w transpose x somewhere, probably it can be very easily extended to w transpose x plus b, or in other words, these two can be very much equivalent. So many people in many textbooks don't use this w transpose x plus b form. They just use w transpose x as a linear discriminant. So there's no difference between these two. It's a very subtle point. If you don't want to pay attention to it, that's fine too as well. But if you ever come across this thing and you're wondering where did your bias term go, it can be made a part of this weight vector to provide a more compact representation. So what our goal is the following. We want a function so that all examples in the training set that have a positive label, so if these are positive examples, these are positive label, these cyan circles, then we want a discriminant that such that if you put the features of this particular example into this function, then this produces a score greater than 0 for all of these examples, all of these positive examples. And if you have examples that have been given a negative label, then what we want is that these points, these negative class points, are below the line, so they produce a negative score. So we want to learn, or we want to get these values of w and b, which we don't know in the beginning, such that all the points of one class of the positive class are above the line and all the points of the negative class are below the line. Or in other words, as we've been talking earlier as well, w transpose x plus b should be greater than 0 for all x for which the target label is +1. So if we know that this is an example of positive class, then we want w and b to be such that w transpose x plus b should be greater than 0. And for all negative class examples, that w transpose x plus b should be less than 0, or all these points should be less than, should produce a score, as I call it, the discriminant function score, less than 0. So if we know that yi is equal to -1, we want to satisfy this constraint. And if we have yi is equal to +1, then we want to satisfy this constraint. I hope that is all clear. The goal of learning a linear discriminant is to find these values of w and b based on the given training data set using some error criteria. And next, what we are going to talk about is how do we define what an error is. And I'm going to ask you a series of questions. If you're given a training data set and you know that a training example has a training label of +1, or if, let's say, if you take a more concrete examples, if you are given a classification problem in which there are apples and then there are oranges, then if you're given a machine learning model, you've given your machine learning model an input that is an apple, the output of it should also correspond to an apple, right? So if a training example has a label of +1, then its discriminant score f of x should be less than 0 or greater than 0. You can pause the video and answer this question if you'd like. And I hope you have answered it correctly. The answer to this is very simple. The discriminant function score for a positively labeled example should be greater than 0. Similarly, I'm going to pause again and ask you this question, or you can pause the video while you answer this question. If a training example has a label of y is equal to -1, then its discriminant function score should be, and you can pause the video if you want to answer. The answer is, of course, should be less than 0. So all negative points should be below the line, all positively labeled points should be above the line, and we can combine these two constraints that we have into a single constraint or a single expression that says this. So if we have a positive example, then the output should be positive. And if we have a negative example, then the output should be negative. Thus, whenever that case is not satisfied, we have an error. So we have an error, we have a misclassification when the output of the from the machine learning model, which I call f of x, or the output of the discriminant function is greater than 0, but the corresponding label was plus 1. Similarly, we have an error when the output is negative, but sorry, I messed up here. So this should be minus 1, and the output should be output if the output is negative and the corresponding true label is positive, then we have an error. Okay, so this is the definition of what we call a misclassification. A linear discriminant misclassifies an example if for positive examples, it produces a score that is negative, and for negative examples, it produces a score that is positive. In other words, we can combine these two into a single definition of an error. We have an error, or a discriminant function produces an error whenever this constraint or this expression is satisfied. So whenever the product of the discriminant function score f of x for a given example x with its corresponding label is negative, we have an error. And if you look at these two, this one and this one, this bit over here is just a compact way of representing these two constraints. So what we have done so far is we have formalized what we mean by a misclassification error. A misclassification error occurs when we have, for a binary classification problem with positive and negative labels, with a positive class and a negative class, if the product of the label of an example with the discriminant function score is negative. Whenever that happens, we have a misclassification error. If the product of y and f of x is greater than 0, then I can say that this example x is being classified correctly. Since for the training data set, we know the training labels and we know the example features, we can plug in this x into the discriminant function score, and we can check whether each example is being misclassified or not. And the goal that we have in terms of building a machine learning model, we want a function f of x that does not misclassify. So we want to reduce the number of misclassifications. We want a value of w and b, or we want such a function f that does not produce a large number of misclassifications. So what we want to do is we want to optimize the number of misclassifications. Okay, so if you consider a single example, then we are going to formalize this further in what is called an error function or a loss function. And we can define that if the discriminant function score and the product of discriminant function score and y, the corresponding label of an example, is positive, then there is no error. Okay, so if f of x is greater than 0, and the label of that example is also positive, so that is a correct classification, so there is no error. If f of x is less than 0 and the label of that example is minus 1, then the product of these two will again be greater than 0, so there is no error. So I hope you can understand this part. The other part is when we do have an error. So we have an error whenever f of x is less than 0, but the corresponding label is plus 1. And we have an error when we have f of x greater than 0, but we have y is equal to minus 1. So whenever that happens, we have an error. So this is our error definition function. We say that we have an error when the product of y into f of x is greater than 0. Oh, so we don't have an error when the product is greater than 0. And if we have an error, so it produces a 1 at the output for a given example, if the product of y and the corresponding discriminant function score is non-positive, or if it's less than 0. Okay, so this indicator function that indicates when we have an error is called an error function or a loss function. Okay, so the two inputs into this function, into this loss function or this error function L, are the discriminant function score of a given example and the corresponding label of that example. If these two match up in terms of their sign, then we don't have any error. But if they don't, if f of x is greater than zero for an example that is negative, or if f of x is less than zero for a positive example, then we have an error. Okay, so this is what is called a 0, 1 loss function or an error function. And we can draw this, or we can plot this function. On the x-axis, we take the product of y times f of x for a given example. On the y-axis, we take the loss function value. And if you pay attention to this equation over here, you can simply map it to this plot. For cases in which the product of y into f of x is greater than 0, you don't have any error. However, if you have the product of y into f of x is less than 0, then you have an error of exactly 1. So for a given example, we can determine using this function, this 0, 1 loss function, whether that example is being classified correctly or not. Now if you're given a bunch of examples, then what you can do for a given line or for a given discriminant function, you can go ahead and apply this discriminant function, or sorry, this loss function, and you can determine how many examples are in error. And that would simply be a summation of the loss function values for all examples in your training set. So if we indicate a given example in your training set as xi, then what we do is we compute the discriminant function score of that example, and we compute the loss function with the corresponding target value or the label, and we sum it up for all examples in our training set. So this is simply a summation of the losses for individual examples. And what this tells you, or what this gives you, is how much error or how many errors does your discriminant function give for a given value of weight and bias parameters. So this is defined as the overall error. So what we have done so far is the following. We have represented our examples in terms of features. We have represented the discriminant function or the classifier as a linear function. So that's the representation part. And the next part we have done just now, is we have defined what is the mathematical representation of an error. And that's pretty simple. Whenever the output for a given example of the discriminant function for a given example matches the target value in the training data set, we say that we don't have an error. Otherwise, we do have an error. And what we have done over here is build a mathematical representation of that thing. We have used the 1,0 loss function that is on your screen in order to calculate for a given f how many examples in the training set out of all of these n examples are in error. Let's say if we have 3 examples, or let's say if we have 4 examples, one example over here, the second example here, the third example here, and let's say the fourth example is from a different class over here. So let's say that features of this is 0, 0, 0, 1. The feature for this is 0, 0, and the feature value for this is 1, 0, and the feature value of this is 1, 1. And we have a line that goes through over here, let's say. Then we know that this point, this cross point, this point over here should be above the line, and it is above the line. The target value of this is +1, as we've shown in on the previous screen as well. And the target values or the labels for these 3 examples are -1. So this is being classified correctly, whereas these 2 examples are being misclassified. So the loss function that we have is going to produce a 0 value for this one, because the discriminant function, this line, this point is above the line. So the discriminant function value is going to be positive. The label of this example is also positive. The product of those is going to be positive. And once we have that positive product, the output of that loss function is going to be 0. However, for these 2 cases, for this example and for this example, these are examples of the negative class, but they are above the line. That means the discriminant function is going to produce a positive values for these 2 examples. Therefore, for this example, the loss function value is going to be 1, and the loss function value for this example is also going to be 1. For this particular example, it is a negatively labeled example, and it is below the line. That means the discriminant function value is negative. So the discriminant function value multiplied with the target label, both of them being negative, will produce a positive product. Hence, the loss function value for this is going to be 0. If we sum up all these losses, this one for this example, this loss for this example, this loss for this example, and this loss for this example, we would get 0 plus 1 plus 1 plus 0. And that tells me that total number of misclassifications is equal to 2, which we can see very easily in this particular case. So with these two examples, this example over here and this example over here are being misclassified. Therefore, the overall loss for this example, for this particular line, for this training data set is equal to 2. Now, if we change this line to, let's say, this line, I would welcome you to calculate exactly what would be the loss for this case, for this particular line. Let's call this line L2. And you can pause the video as you go ahead and calculate this yourself. But I think it's really easy for everyone to see that this is going to produce a loss of 0 for this example, L2. It's going to produce a loss of 1 for this particular example. And it's going to produce a loss of 0 for this example and a loss of 0 for this example. Therefore, the total loss for this L2 line is going to be 1. So this is going to be a better representation of, or a better classifier over this training data set in comparison to our other line that we have taken earlier. So I hope this helps you understand the overall concept of what we are trying to do over here. We have done representation, we have done error formulation, and then the next step is we are searching for that line. We are changing that line, and we are trying to find those values of the weights and biases that give us the lowest error, and that is the optimization part, and that is where gradient descent is going to come in. However, there are a few problems with this particular loss function, and that's what we are going to discuss. If you take a look at the plot for this particular loss function, this 0, 1 loss function, you can see that it's a sort of a step function, right? And what that means that the derivatives of this function, which we would need when trying to minimize or trying to optimize this function, or when we are trying to calculate the gradients and gradient descent, are not going to be particularly well defined at this discontinuity. Okay, so there's a discontinuity in this function, and that leads to a problem. Another problem that we see over here is that this particular loss function is not convex. So if you take a line between any of these 2 points, we can see that this function is not convex. And then that means that gradient descent may not give you an optimal answer for this particular loss function. If you're trying to minimize the overall loss using gradient descent, then this loss function is not a good choice because it's not convex. Okay, so that is the problem. Those are the associated problems that we have with this 0, 1 loss function. What we want to do is we want to find the parameters w and b of the discriminant that minimize the loss for all examples in training. However, since the 0, 1 loss is non-differentiable and it is non-convex, it leads to poor optimization. So we'll not be able to use, or the convergence of gradient descent will not be guaranteed if we want to solve this optimization problem using gradient descent. Okay, so instead what we propose to do, or what the original creators of what is now called the perceptron did, is that they came up with a convex approximation of this 0, 1 loss function. So on this screen, on your screen, you can see the original loss function, the 0, 1 loss function, as a dotted line. And what we've done is we have built what is called a convex over approximation of the 0, 1 loss function, which is called the hinge loss. Okay, and it's called the hinge loss because if you think of this as a door, then this is a hinge over here right now. Okay, so it can move around that particular location. So what we have done over here is we have built a convex over optimization of this loss function, of this 0, 1 loss. And what that essentially means is, first of all, it's convex. So if you take any 2 points on this function, this new function, the green function that you see, and you connect them, you can see that the line is always above that particular function itself. So it's convex. There does not exist any line that doesn't lie over or on the function itself. Okay, so it's a convex function. So that's the good thing about this one. It's convex, And another good thing is that it's differentiable. So it's you can take derivatives. There is no discontinuity like we had in the 0, 1 loss function. Okay, so this is a good approximation of this, but we don't know the equation of this one. And that is a problem. And that's a problem we can very easily rectify. So we know that the mathematical formulation of the 0, 1 loss is simply L of f of x comma y is equal to, it doesn't produce any error if the product of y into f of x is greater than 0, and then it produces 1 if y of into f of x is less than 0 or equal to 0. Okay, so that was the definition of 0, 1 loss. So I'm going to call it L01. Okay, so that's a, or you can call it a step loss. So that is the error definition of this, or the mathematical representation of this step loss function. Now what we want to build is a mathematical formulation or the mathematical equation of this green line, and that's not too hard as well. For that, I'll draw your attention to this thing on the right hand side. So let's say if we have a function like this, it's exactly the same function like the hinge loss function that we have shown over here, but I've done a change of variables. So I've plotted a variable z on the x-axis, and then we have this purple line that tells us the value of this function that we call L of z. Okay, and we know that this function, this purple line, has 0 value along the y-axis for anything that is greater than 1. So L of z, we can say that L of z is simply equal to 0 whenever z is greater than 1. Okay, and what about this part over here? That's the part that we are left. So what happens when z is less than 1? Okay, and that's easy to figure out as well. It's a line with a slope of -1, and we know that because it intercepts the y-axis at this location, and then it intercepts the x-axis at this location. And we can use a 2-point form to find out direction, to find the equation of this line, and that comes out to be nothing but 1 minus z. Okay, and we can verify that if you put z equal to 0 in this function, then it comes out to be L of z comes out to be 0. And if I put z is equal to 0, which corresponds to this point, the output of this becomes 1. So this L of z is equal to 1 minus z is this particular line. So we can simply write it as a piecewise function. L of z is equal to 0 whenever z is greater than 1, and L of z is equal to 1 minus z whenever z is less than 1. Now, if you compare this thing over here to this thing over here, the only difference is that we have done a change of variables. So z is equal to y times f of x. And if we put that, then what we get is essentially this thing. This hinge loss function is going to produce a value of 0 whenever z is greater than 1. And instead of z, what we have done is we have put y times f of x greater than 1. Okay, so that's good. It's the same thing. And then the bottom for the other part, we have 1 minus y times f of x. So you replace y times f of x with z. So we have done that. And then what we get over here is the corresponding other part of this from this function. So this equation over here that you see is the mathematical representation of this hinge loss function, which is convex and which is, well, we can differentiate that as well. So this is nice. Then we can go ahead and optimize it, as we'll see in just a moment. However, we can make this even more compact. So we can say that the loss function value is 0 whenever 1 minus y times f of x is less than 0. So this is a simple rearrangement of this thing, and you should be able to figure that out pretty easily. And the other part is, the other thing is, this remains the same, and we can say that for the other part, whenever 1 minus y times f of x is greater than 0, then the loss function value becomes 1 minus y times f of x. So this is a simple rearrangement of this thing over here. We can also even simplify it further as the following loss function. So this is all change. This is basic manipulation, or nothing too fancy going on here. It's just we are trying to come up with a more compact representation of our loss function. And this is another compact. This is a compact representation of the hinge loss function. So the hinge loss function is 0 whenever 1 minus f of x is negative. Therefore, whenever 1 minus y of x is negative, the maximum of 0 and this value is going to be 0. So it's going to produce a 0 over here. Whenever this number is positive, or this part over here is positive, then the output is exactly going to be equal to this. So this is a mathematical representation of this function over here. And that's pretty easy. So what we have done so far is we have built a convex over approximation of the 0, 1 loss, which is convex, and we can differentiate it as well. Okay, and we'll need to differentiate it because we were interested in minimizing the amount of error over the training data set that a particular line produces. And for that, I am going to first write the optimization problem. And this is the optimization problem that now we want to solve. Okay. So we are given a training data set in which we know we have a bunch of examples and we know their labels. We are given a discriminant function which is based on a parameter value w, which is the weight vector, and we want to minimize this loss, or we want to minimize the sum of misclassifications or sum of loss functions for all of the individual examples. So if we have 4 examples, then in that case, n is equal to 4. And let's say if we plot this, if we take the and classification example, we have 4 examples in that case. It's a very simple training data set. We have a feature vector of 1, 1 there. We have 1, 0 here. We have 0, 1 here, and we have 0, 0 here. And we know that the corresponding labels for this is -1. The corresponding label for this is -1 as well. The corresponding label for this is -1, and the corresponding label for this is +1. Let's say if we have an equation, if we have a linear discriminant, okay, and we can write that as w1 x1 plus w2 x2 plus b equal to 0, then for a given value of these features, for a given example, we can calculate what is the discriminant function score, and then we can substitute that discriminant function score into this equation over here, and that is going to give us how much error is there for that particular line. Okay, so you can calculate in the same exact manner the overall error that, let's say, this discriminant function produces that I've just drawn on your screen. And the overall error is going to be the sum of errors over individual examples. So how much error does this example cause with this discriminant function? What is the corresponding error for this particular example with this discriminant function, and so on? And we sum up all of those errors. So it's just like tuning a radio. If you pay attention to it, if you think about it, we want to change the values of W and V. We want to change the line so that we are able to minimize this error. So we tune to the right station, okay? And we can minimize this using gradient descent. So this is the optimization problem that we have in front of us. So I'm going to say something that is going to be true for almost all machine learning models. All machine learning problems can be expressed as optimization problems, and that's what we'll do throughout the rest of this module as well. And once we have a representation of a machine learning problem, we have represented the features, we have represented the discriminant, and we have defined what qualifies for an error. That is what we did in the last step. We said that we are going to measure errors using the 0, 1 loss function, but we couldn't do that because it's not differentiable. And so that is going to lead to complex optimization problems. So we have simplified that or built a complex over approximation called the hinge loss for that purposes. And then the next step is we've expressed that training problem in the form of an optimization problem, which we can now go ahead and solve using gradient descent. And that's what we are going to do. So this is going to be a consistent theme throughout this module, and it's a consistent theme throughout machine learning and data mining. We are given a statistical learning problem, we represent it, we define an error on top of it, and we express it as an optimization problem, which we go ahead and then solve using an optimization algorithm, such as the gradient descent. Now, what this allows us to do is that we can do this for any arbitrary number of examples, even if the number of examples is very large. since we have a mathematical representation, we should be able to program it and we should be able to work our way through an algorithm to the solution of this problem. Similarly, it doesn't matter how many dimensions it has. Of course, that's going to increase the computational complexity of the problem that you are working with, but still, you will be able to solve much larger problems than you are with your hands only or with using geometric approaches or even algebraic constraint satisfaction, just like we had done earlier. Okay, so next what we are going to do is to apply gradient descent. And how we're going to apply gradient descent is the following. So we want to find the weight values W that minimize this loss function given a training set and the corresponding labels. So what we express is first we express the mathematical function. We know that the overall error for a given training data set for a given parameter value of the discriminant is given by this summation. So it's just the sum of the loss values or the error values for each of those individual examples, and we have a mathematical representation of that. And then what we can do in gradient descent, we take the derivative of the loss function with respect to the variable, or we take the derivative of the target optimization function with respect to the variables of interest. And then we get the gradients. And once we calculate the gradients, we take a step in the direction opposite to the gradient. That is what we do is we go ahead and change the value of W based on that gradient. So first we need to calculate the gradient of this beast over here, this equation over here. So we know that the gradient of this loss is simply going to be the gradient of the losses over individual, or the loss function over individual examples. So what we need to do then is to calculate this thing, this loss, the partial derivative of this loss or the gradient of this loss function with respect to our W for a given example. Let's say if we have an example X, then we can express the gradient in the following way. We will be taking the derivative of this function over here, which is the loss or error function with respect to a single example with respect to the weight vector. And it's very easy to do. If you take a look at this function, this mathematical representation, this geometric representation of this mathematical function, we know that the derivative of this function, this loss function, in this region, when y of x, f of x is greater than 0, is always going to be 0. So because the function value is 0, so if you take the derivative of that, it's still going to come out to be 0. Okay, so that's what we get over here. Since the loss function, since this part of the loss function corresponds to 1 minus y of f of x, so we can take the derivative of this with respect to W, 1 minus y times f of x, and we know that f of x is nothing but W transpose x. So what we will do is we'll substitute that in. So I'm going to put this in, and we get 1 minus y times W transpose x. And if you take the derivative of this, it's simply the first part of this one, the derivative is going to be 0 because that is a constant, and then we get the derivative yx. So W goes out, just like you would take out a scalar variable. You take a derivative with respect to it, it would just vanish. So the gradient of this loss function in this case is going to be minus y times x. So we can rewrite this. So whenever the loss function is positive or non-negative, we have the corresponding gradient is going to be y times x. Otherwise, the loss function value is going to be, the gradient of the loss function is going to be 0. So I welcome you to calculate this by hand and try to understand this. This is really easy. So what we have done so far is the following. We have defined the loss function for a single example, and we want to reduce the loss, or we want to reduce the error. I'll keep on using these two terms interchangeably. We want to reduce this error, and the way we do that is that we take the derivative of the error with respect to the weight functions that we can tune, and we can do that using gradient descent. So we compute the gradient of this, which comes out to be this function over here. Okay, or you can say that it comes out to be this function. If the loss function is positive, the value of the loss function is positive, then the gradient is equal to this. Otherwise, the gradient is equal to 0. Okay, so that's pretty much it. And if we put that, now we should be able to build an algorithm. So the overall error that we have is this thing. This is the error across all examples. And this is the gradient with respect to a single example. So now we can build an algorithm by combining gradient descent-based optimization for our learning problem. So this is what is called, loosely called a perceptron, by the way. So I didn't want to give it a name before we built it. So what we've done is built it from scratch. So we're given a training data set in which we have training examples. We have n training examples. In the AND classification problem, we had four classification examples. Each of those examples has a set of features which were in 2D for the AND classification problem. So we can say that for the AND classification problem, xi belonging to a two-dimensional feature space. So we can say that xi belongs to R square. So that's, if you see that in a book, don't be confused. What it means is that there are only two features. In general, if you have D features, then we are going to say that this is D-dimensional. And for each of those examples, we have a corresponding label, which can either be negative for negatively labeled examples, or it can be positive for positively labeled examples. And we have studied gradient descent. What gradient descent requires is a starting position. So we need a starting weight value, which can be picked randomly. And then what gradient descent does is that it calculates the overall error for a given example, or it calculates the function value that we want to optimize. We calculate the gradient of that function, and then we take the step opposite to the direction of the gradient. So if you want to remind yourself of how gradient descent works, the fundamental equation of gradient descent is the following. We assign wk to be the previous value of k minus alpha times the gradient of the function that we want to optimize with respect to w. So this is the fundamental equation of gradient descent, okay? And what we will be doing is we'll be using this equation. So what we do is, if you are given n training examples, we pick a single example, we we use our discriminant function or the current value of w to compute the output of the output discriminant function score for that particular example. So this should be there should be an I over here. Sorry for the typo. So we have that score, and then once we have that score, what we do is we calculate the gradient. And if you notice over here, the gradient of this particular loss function is minus y times x whenever the loss function value is greater than 0. So whenever you make an error, only then do you need to calculate the gradient and update your weights. Otherwise, the gradient is 0. So you don't need to update any weights. So this is what is being checked over here as well. If yi times f of xi is less than 1, then update your weights using gradient descent, which is this equation over here. You have the previous value of weights, and on the basis of gradient descent, you calculate the loss value or the gradient of the loss value, and you take a step by an amount alpha along the direction opposite to the gradient. So that's why we have a minus over here. And you get a new value of this k. So that's what we'll be doing, and this should be minus 1 as well. Okay, and if we substitute the value of the gradient from the previous equation, which is simply minus y times xi, you end up with this beast. It's a linear equation, it's not exactly a beast. So you get wk is equal to wk minus 1 minus alpha, so minus alpha, and this minus y times yi xi is coming from this part over here. Okay, and what that means is we have an algorithm. We will keep on doing this in a loop and until we converge. And the convergence is simple. If there are no losses, if everything is being classified correctly over the training data set, we stop. And this algorithm was developed in the 1960s. This is one of the first neural networks out there, and it's called a perceptron algorithm. And next, what we are going to do is we are going to try to implement this algorithm in Python.